Okay, this is lecture number 11 on neutron diffusion, the sixth in the series of diffusion. And in this lecture, I'll be talking about the applications in criticality. The course is NE402 Intermediate Nuclear Engineering, covering diffusion and transport of radiation, as well as Monte Carlo simulation. It's a full 15 weeks. It's a full semester, 15-week course based on a total of 45 lectures, and I try to do each lecture of around 40 minutes to fit into one standard lecture. So let me just give you some idea what, so here's my name, telephone number, personal address, official address, and website. Now, last time I had discussed with you two group equation for both multiplying and non-multiplying media. So now this was the case that I last discussed with you. The two group equations were a core and a reflector. So these are the four equations that I showed you in the previous lecture in two group diffusion, equation in a reflected system, a core reflector. And today I'm going to show you in this lecture the applications of this by which we can estimate the size or composition of critical assemblies. So this lecture I'll take you to some practical aspects, and so the first thing I'm going to do basically is a kind of connection with the criticality condition, this one, that you get the conditions from which either you're given the composition and you have to find the dimensions, or you know the dimensions and you have to find the compositions. So you specify the dimensions and you have to find the composition. Okay, so let me now go to a criticality method. So let me start sharing this with you, another document, so you get some idea of the practical side of things. So this is, I'll just take you through 4 or 5 pages from the Los Alamos report, LA14244-M, approved for public release. Distribution is unlimited. So I hope I'm not, this is just for educational purposes. And now these are the things that you value as an undergraduate or graduate student. And if you're given an exposure to the practical applications, and you don't have to wait so many years into your career to realize that those equations which you learned were applicable over here. So, so this is the report. It's an excellent report, and it's a fairly big report. It's got 180 pages, and I really liked it. So I'll just show you that what do they do for hand calculation methods for criticality safety. Safety is such an important thing. How do you store materials? And this is some work that I also did in my career. And so I really value these things, that how important they are, especially when I worked in a centrifuge plant and at various stages as the enrichment changes, then we had UF6, and how do you store cylinders, and as the enrichment gets higher, the cylinders get smaller, and then the storage in a room has to be done so that the people working there are safe. So the table of contents of this report, that this is the main thing I want to show you, that one group and modified one group diffusion theories are used. And so they're using over here one group diffusion theory and modified one group diffusion theory. And I just want to show you 2 examples from here. This is an excellent report. It's available on the net. So I would recommend interested students to spend a weekend on this. Okay, so let me take you to page 4 of this. So this is page 4. Now let me take you to page 11 of this report and an overview. Overview, now exactly the things I've been talking to you about. One group diffusion theory and one group modified diffusion. Now what does modified diffusion theory, one group, mean? It means that you have the non-leakage probability e to the minus b squared tau, and you have the thermal non-leakage as 1 1 over 1 plus L square B square. So you combine the L square and the tau, and you say that for large reactors it is M square, a migration area equivalent, and you get an answer much better than what you would get from a simple one group application. Now, this is for single unit methods. Now, often for those of you who go and get a job in an enrichment plant, in a reactor where you have to store materials, then whenever you place things, then you know things interact, they talk to each other. So there's a solid angle method because there's interactivity. So what is the limit of safety when you handle these kind of things? Okay, so this is page 11. Now let's go to the next page, 12, and let me show you. This is an excellent report, and what I like about it is that it connects classroom teaching with uh, real life problems. So remember I told you that whenever you talk about these things, then always say what assumptions are implicit in the model and what is the applicability. So this is what this report does so nicely, that the one group and modified one group diffusion theories are good for large homogeneous systems with isotopes that have low neutron absorption. So important. Caution, diffusion theory is not a good method to use for small systems or near boundaries or in a near strong neutron absorbing material. Now, that's exactly what I told you in the last lecture, that, and for that you have to wait for lectures on transport theory, which I'm going to give for the next week. Okay, so you can do buckling conversions are useful for simple geometries. Now I call these regular geometries, and there's no such restriction when we come to Monte Carlo simulation. So the restriction over here is that they're used for uniform geometry. But in real life, you don't have uniform geometry. So I'm going to show you applications where we're going to design, especially small space reactors, because now there's going to be a big market for SMRs, small portable reactors, and I think that's the future of nuclear engineering. So you've got to learn how to design small systems. Okay, so here I'm going to show you an application so that you develop some confidence. Now this is for array hand calculations. So I'm not going to go into arrays because I've just started teaching this course to you and I want to keep things simple to give the concept. But solid angle, yes, we're going to talk about it. It's call it a view factor, and that's how things talk to each other. MCNP, you can see over here, is so widely used Monte Carlo and particle code, and this is exactly what I'm going to talk about in the coming weeks. Okay, so here are all the equations of the one group and modified one group diffusion theories that I was talking to you about. I started deriving this with you in, I think it was lecture 6 or 7, d del square phi minus sigma a phi plus k infinity over p phi, and I put that equal to 0 and made it a steady state case. So this is exactly what is being done over here, a balance equation, a continuity equation, and this is applied. You've just got to put the right data in here. This is the del square phi plus b square phi equal to 0. You can see b square could be a material buckling or a geometric buckling. Now for criticality, this is the material buckling, which has got to be equal to the geometric buckling for regular geometry, meaning slab, sphere, and cylinder. Now these are the solutions. They're applying the boundary conditions. This is the flux for symmetry, as I told you. This is the physical boundary, these two vertical lines, and this is the extrapolated boundary where the flux goes to 0. And the extrapolation distance is being used as 0.71 times the transport mean free path. These are the same constants which I showed you the derivation of. And let's come to some practical thing what they've done. So they have, I just want to show you some of the legacy assemblies that were done. And I want to show you an application over here. So this is the non-leakage probabilities. Now here's the applicability. So applicability example problems. So let's look at the first example problem that is done over here. So you can see it's diffusion theory example problem number 1. Now assume a slab tank, figure 2, containing a mixture of water and pure plutonium-239. Now, this is what I told you, that remember when we did the example of U-235 and water? So this is a similar problem of plutonium-239 in a water tank, and the concentration here is 100 grams per liter. Now, liter, you know, is 1,000 cubic centimeter. They've given the temperature, and what they want to find is, using the data in table 3, determine the following for this particular system uh, to support the design for a slab tank that will contain a pure plutonium solution. So you're supposed to find the K infinity and the critical slab thickness using one group diffusion theory, and you're supposed to repeat that using modified one group diffusion theory. Now, these are very good exam problems, and when I make an assessment exercise for you over here with MCQs and questions and exams, so I'm definitely going to have something like this for you to do. So this is for U239, this is for water. So this is the microscopic cross-section data given over here. So you can use it. I gave you data for 235. Now, remember I told you that when you go down to thermal energies, then there's a Maxwellian. So this is the correction factor for 1 over V. And if like plutonium-239 is a non-1 over V absorber, so you use another correction factor for the thermal evaluation at 2200 meter per second. Now 2200 meter per second is 0.025 eV. So they find the average absorption and fission cross sections at thermal energy. Same thing for water. And this is what I introduced to you in lectures, I think 2 and 3, how to find the number density from Avogadro number. So you repeat the same thing over here, and you find the four-factor formula. Remember, it was epsilon p eta f. So this is the epsilon is about 1, then they've assumed that p is about 1. So they say that because there's no fertile material present. Now there's fissile material and fertile material. Fissile are Pu239, the odd ones, and the even ones are fertile. Fertile basically spoil the situation, plutonium-240 and all, and especially there's some problems with it which I'll go into later. But this is the four-factor formula with epsilon and p set to 1. So you're just left with eta and f. So eta is nu sigma f over sigma a, 2.061, and F is the thermal utilization in the fuel, which means sigma A in the fuel plus sigma A in the fuel plus any other thing which is non-fuel. So let's call it the mixture in this case, plutonium plus water. So plutonium absorption divided by plutonium plus water absorption. Remember, these are like 92.5% of the neutrons are relevant to plutonium-239, the others are not. So K infinity comes out to be 1.906, which is a good number, in the sense that when you multiply this by the leakage probabilities at fast and thermal, so you're supposed to get 1. So what you need to do is to find that system whose leakages, when you multiply by the K infinity, then whose leakages would give you a K effective of 1. Okay, so that's the important thing over here. So this result for K infinity means that criticality is possible. Now, if this number was less than 1, then I tell you that we cannot find a critical configuration for these number densities. So then you'd have to increase your number density. So if I give you an exam question and I say that find K infinity and tell me what is the critical configuration, and in your problem you find that it's 0.95, not 1.9 or not something much greater than 1, then you're going to have to tell me that it's not possible to design with the values that you have given, so I'm going to increase the concentration of the fissile material. Okay, so here they do the K infinity, then they calculate the L square from L square, which is the diffusion length square, which comes out to be 0.611 centimeter square, such a small area. So if you take the square root of that, that's about 0.8 centimeters and less than 0.8. and this is b square, which is k infinity minus 1 over L square. So this is what we call the material buckling. The material buckling uh, is a number which we've got to put equal to the geometric buckling, which for a slab is pi over a bar square. Now notice it's a bar square, a bar meaning that the extrapolation distance is included. So when we put the b square of material equal to the b square of the geometric buckling, then we are able to find the dimension a bar as 2.58 centimeters. Now, when I find a bar, so now I've got to find the extrapolation distance, which comes out to be this much. They've used a value of 2 times, of 2.13 times d. So it was like 0.71 times lambda transport. Lambda transport is the inverse of sigma transport, and sigma transport is 1 over 3 times the diffusion coefficient. So this number over here is 0.71 times 3. It's 2.13. So this is the diffusion coefficient. So when you put them equal, so here's what I get, that 1.9 centimeter is the critical dimension. This is for a plutonium metal water mixture with the given concentration that you used. So, uh, so essentially, this shows that the critical slab for this concentration is about uh, 5.6 inches, 14.2 centimeters. Okay. Okay, so I'm sorry, the figure 3 shows that the critical slab would be 5.6 inches. So this result shows that simple one group diffusion estimate does not accurately estimate the critical dimensions for the slab. So let's go to the modified one group diffusion, because that did not look at the slowing down. So now if you include the slowing down, so then you can see the estimate we get is 17.34. So the extrapolation distance, if you take out 2.14, so you get something like this. And the so this result is a bit better. So it compares well with the infinite slab. So let's look at the numbers over here. Now you can take different values. So this is a plot of the critical infinite slab thickness. Infinite meaning in the y and z directions. Okay, this could be a misleading term. When I was a student, I used to say, why are they saying a critical infinite slab of thickness anything? So if it's infinite, then how could it have a thickness? So it's infinite in 2 dimensions, in the y and z directions. That's an assumption. And this is, which means that the one-dimensional theory does not know how to estimate dimensions in the other direction. So for that, you'll have to extend the diffusion equation into 3 dimensions. So now look at this. On the x-axis, you've got concentration of plutonium in grams per cubic centimeter. And remember, it was grams per liter. So we had grams per 1,000 cubic centimeter. On the y-axis, it shows you the slab thickness in inches. So this is the case. So this is 5 weight percent of plutonium. This is 0. Oh, sorry, this is 0 weight percent of plutonium-240. So let's look at this graph. Now this graph for this give you a 5-inch thickness for this kind of a density over here, right? So you can see that as the concentration of plutonium gets less, so the critical thickness required is more. And as the concentration of plutonium gets more, so the size becomes smaller and smaller. Size is on the y-axis. So the size becomes smaller. And it also depends on the percentage of the bad stuff. Now the bad stuff is plutonium-240. So plutonium-240, if you have like 20%, and if you don't have any, for the same concentration, see it was 6-inch thickness over here, and now you require almost an 8-inch, 7.5-inch thickness. So that spoils the show. Okay, so you can put in the example that is given in this report. You can put in the various concentrations, and you can write a little MATLAB program, and you can reproduce this. So I'd say you should do this, and this is for an unreflected uh, core, infinite slab. Okay, now let's look at, I want to show you page 38. So this is now a fissile system made up of a bare sphere of sodium and plutonium. Now this is a fast core because there's no hydrogenous material in here. So again, given this data using one group, the question is estimate the critical radius and what is the probability that a neutron will leak out of the system. So what do you think the probability relevant to this is? Of course, it's the fast probability, it's not the thermal probability, because you're not going to have any thermal neutrons. So I won't take you through that. Now let me bring you to problem 4. Now in the early days of nuclear engineering, let me try to make this a little bit smaller so you get a better view. Okay, now look at this picture carefully. This is the Jezebel critical assembly at Los Alamos. Now there was Godiva, Jezebel, and Topsy. So if you see, this is parts of a sphere. This is the lower, that's the upper, and that's the middle section. So they carried out lots and lots of experiments at Los Alamos from which the whole world learned about criticality. And I must say the scientists and engineers of that age uh, gave so much to humanity that they really taught us. And one of my professors at Madison, Charlie Maynard, from whom I learned Monte Carlo simulation, the late Professor Charlie Maynard at University of Wisconsin-Madison. When he was a young man, he worked at the Manhattan Project and used to tell us stories of that. And they were fabulous people who set up and gave the whole world this new technology. Okay, so let's look at this problem number 4, that how do we estimate the criticality. Now you know that plutonium is something which was made by, I think, the first chairman of the US Atomic Energy Commission. And yeah, so he made the plutonium for the first time. And so plutonium comes in, has some metallurgical complexities. And so there's an alpha phase and a delta phase. And their densities are very different. Alpha is about 19, and this is about 15.6. So let's consider the delta phase, which is Jezebel, and it's an unreflected or bare system. So let's see whether one-group diffusion theory estimates the spherical critical radius, because they did so many experiments for this. They know the answer to this. And so here's the data that you take for plutonium-239. Of course, there are other things in it like gallium and other plutonium isotopes. So if you take the absorption, fast, transport, capture cross sections, the nu and the eta values, and the given references over here, this report you can download, calculate the number densities, calculate the macroscopic cross sections, calculate K infinity, and okay, so calculate the diffusion coefficients and get the material buckling and put it equal to the geometric buckling for a sphere. And what you get, so they get a radius of 9.59 extrapolated, take out the extrapolation distance, so it's about 7 centimeters. Now, actual Jezebel had a density of 15.61 gram per cubic centimeter. It was 4.5% plutonium-240, which is not considered here. It had a critical radius of 6.38. Not bad. So 6.38, 6.93. Excellent. So with these cross sections and assumptions of 100% plutonium-239, so as assumed in this calculation, this method slightly over predicts the critical radius for this type of a system. So I would say it's excellent, excellent. And so now you can look at Godiva also. This was the uranium sphere that Los Alamos did experiments on. This is also so well documented in the literature. And this, I must say that it, it opens your eyes when you get to realize that it's such a fascinating. So here, from here you get 8.44 centimeter, and I think it's 8.710. I almost know that by heart. So let's see if it's 8.710, but they haven't said it here. Okay, so Godiva and Jezebel are here. Now let me do a new share with you. And I want to show you another report uh, by De Volpe. So let me share this report by, sorry, let me have a new share and let me show you this report, which is also available on the net. And I hope you can see now this journal article of 1970. So it's a journal article of, sorry, 1982. Okay, so it's in the it's in progress in nuclear energy, volume 10, number 2, pages from 161 to 220. It's a very comprehensive article, and it talks of denaturing fissile materials. So on this, I want to take you to page 13. Now, I was just talking to you about Godiva and Jezebel. So if you look over here or on these two figures, so all those calculations of one group and modified one group you can do. This figure shows you the dependence of plutonium critical mass upon fissile fraction. So when the fissile fraction is 100% over here, which means, and these are the two phases. This is the alpha phase. You can see it has a density of 19.5. If I make this a little bit bigger, so you can see this has a density of 19.5 grams per cubic centimeter, plutonium metal. While the delta phase, and I'm not a metallurgist, so I'm not really sure about how the alpha and the delta phases uh, differ actually metallurgically, but I just know that their densities are very different. I have not uh, much knowledge on plutonium, so so what you can see over here is that if you have 100% delta phase plutonium, then what is, so it's a little bit less than 20 kilograms, the critical mass. And if you have 100% of the alpha phase, so it's like 11 kilograms. And when it's diluted by this bad stuff, plutonium-240, which gets produced by capture in 239, and this is usually a nightmare for engineers. So because it's a spontaneous emitter and it causes all sorts of problems. Now, spontaneous emitter means you cannot hold it in your hand. Also, it becomes hot, temperature-wise. So if you have 20% of plutonium-240, see the critical mass goes a little bit up. Now, this is the oxide, which is used as fuel in nuclear reactors, which can be used and has been used and probably is used. But fast reactors are very few in the world and not very popular because environmentally not such a good thing. Anyway, but very efficient. So if you see that as your fissile fraction gets less, in other words, your plutonium-240 becomes more, so there's an increase in the critical mass, so more mass is needed. Now, this shows you the dependence of plutonium critical mass upon 242. So you can see that 242 makes things really bad. So if you have a little bit of 242, so it goes up to like, see the alpha phase, if you have 40% of fissile only, 60% of that, then now you need about 40 kilograms of critical. So, so these are all criticality studies which you can do with one group and two. Now, I spoke to you in the last lecture on a reflector. So here I want to show you the effect of a reflector. And here we're using a reflector 10 centimeters of uranium, which is not such a good idea. but these are just calculations. Why is it not a good idea? Because uranium is very, very dense, 18.9 grams per cubic centimeter, as you can see over here. So the mass is so much. So okay, so let's look at the bare U-235 first. This is Godiva. So Godiva has, okay, this would have been Godiva if this was not there. So you can see that, remember, Godiva had 8.71 centimeter radius. Now it's reduced from 8.71 to 5.8 by the reflection of 10 centimeters of uranium surrounding it. So the radius has come down, the volume has come down, the unreflected mass was about 50 kilograms, while the reflected mass, but this includes, sorry, while the reflector mass is 300 kilograms and the core mass is 15.7. So you can see that first you needed 48 kilograms to make it critical, and now you need 15.7 kilograms. So you see there's a reduction of how much? There's a reduction of about 33. It's a huge reduction by reflecting it with uranium. Now look at plutonium-239, what we were just talking about. First started talking about Jezebel, which was the delta phase, which had 15.9 grams per cubic centimeter. Its radius now has become 4.7. There it was about 6.2, and here it's become 4.7. So you see the unreflected mass was 15 kg and the reflected mass is 7 kg. So it's less than a half, which means that you can make you can have 7 kg of plutonium-239 in the delta phase critical if you surround it by 10 centimeters of uranium. The total mass is very heavy, so 250 kg. So do you think you could use it for the Mars mission? Well, in the Mars mission, they're using plutonium-238, which is not shown here, which gives you heat, for which they use a thermoelectric generator. Okay, so I've showed you 235, 239. Look at the alpha phase. Alpha phase requires 11 kg unreflected because its density is much more, and 4.5 kg reflected. And then you can look at other things. U-233 is as good as U-235, not used for other reasons. And plutonium-232, 242, look at uranium-235, 20% enriched. Now 20% enriched has a radius of 16.4. It has an unreflected mass of almost a ton, and you can reduce it to 350 kg if you surround it by 1110 kilograms, over a ton of kilograms, which means that you're not going to be able to transport it easily. Now, similarly, you can see the depleted grade plutonium. So you can see all these numbers here. Now, let's look at a better reflector, beryllium. Now, remember I told you U-238 is not such a good idea. Beryllium is a better reflector. Why? Because it's lighter. So if you look at the critical masses over here, so let's look at plutonium metal. Which phase is this? Is the alpha phase. So they're not showing the delta phase in this figure. So in this figure, you get to see the alpha phase of plutonium, which has a density of 19.5, diluted by plutonium-240. You see the metal 235 of uranium and surrounded by 10 centimeter beryllium. So look at this, 4.5 kg makes it critical. And here, less than 20 kg makes it critical, compared to 50 kg before. And this, of course, is the variation as you go left, as the fissile fraction gets less. Now, this is for uranium metal. Nobody uses uranium metal fuel these days for reactors, because now you use, then in between they started using uranium dioxide, then uranium dioxide with uranium nitride, and now you've got ceramic fuels. So now we've got lots of advanced fuels coming up. So nobody uses uranium metal anymore. But if you look here at percentage of U235 with critical mass, you can see that with 10, 20%, you need hundreds of kg to make it critical. As a bare sphere, you probably cannot make it critical for 10 or 20 centimeters. But when you surround the uranium metal by 10 centimeter uranium nitride or with 10 centimeter beryllium. See, beryllium makes it less. So when you surround it with 10 centimeter beryllium reflector, then imagine if you had 20%. So that was not possible, the metal. Now 20% gives you about 200 kg. So you can make it with 200 kg, you can make it critical. Now if you have, so this is the reason why people enrich uranium, because you can see that this is the civilian reactor grade, which does not allow you to go beyond 20%. These are the things used for experiments and all, and these are the things used for weapons. So this is weapon grade, this is high grade, and this is LEU, low enriched uranium, and this is HEU, high enriched uranium. Now let's look at critical mass dependence. So these are all sorts of various combinations. So, uh, so this is what I wanted to tell you. I think that what you're studying has direct application in nuclear engineering to be able to calculate, and the reason I'm teaching you this is to be able to design space missions, small reactors which humans will carry to Mars or to the moon or God knows where. So if whenever human beings go out and explore space and find something new, so I'm sure that they'll consider small nuclear reactors, or if they go to remote locations on Earth even. So, but anyway, Moon and Mars, if you want to go and live there for a few months, a few years, you want 1,000 people living there, you want to inhabit these two planets. If anybody ever finds water or traces of life, God knows what lies in the future. Human beings would have come from Mars. We don't know. These are all the big questions. If you find water, if things get bad on this planet, etc., etc. So it's very important to know that you can design small nuclear reactors. Uh, of course, I would not advise that you design small nuclear reactors with plutonium. Uranium is much better. And from here, you can see it's not such a good idea to take reactor-produced plutonium to the moon or Mars, because it would contaminate things and you'd spoil it for yourself. Okay, so I think this is as much as I wanted to discuss one group and two group. Okay, so let's wind up the lecture with some numbers from here. So you can see the critical masses of plutonium, and so fissile fraction as it goes down. So now these are the contaminants and of the fertile, which makes things bad, and you can see that the critical mass increases. So, of course, these are online lectures, so I cannot ask you to ask questions, but I'm sure that a young mind would have so much, and students have so much in mind. But I can tell you, when I was a student, then I was taught the one group and the modified one group and the two group, and this was about in the 70s at Queen Mary College, 1975 to 78, when I did my engineering. And this course was taught by Professor Mike Williams. And in those days, we didn't have the net. So we learned one group. Of course, we didn't have laptops also. So I was not able to do these kind of things as a student. And I had absolutely very little idea how the one group or modified one group applies in real life. So this is the difference of today's education, that you learn something, you learn its application, you've got MATLAB, and you have so much power in your laptop. So for you, you can probably learn in 1 or 2 hours what I took years to understand and appreciate. So, okay, so let's close this lecture over here. In the next lecture, I hope to move to transport theory.